And okay, thank you. All right, so let's keep going. Last time we started describing the structure of all Clawford graphs. So just to remind you, G is Clawford if G has no induced K13, which is this graph. And first I said that people think of Clawford graphs as a generalization of line graphs, and then I said that they're far from being line graphs. And we have this diagram. We said these are line graphs. And then these are what's called quasi-line graphs, which means graphs where for every vertex, the neighborhood is a union of two cliques. But then I don't mean like as two cliques as a graph. I mean, it's two cliques and just as a vertex, right? It's two cliques and you're allowing edges between them. And then we said this is Clawford graphs. And we said there's something here and there's something there. And what was there was a Schläfli graph, which is a nice graph, but I won't mention it again. But what was here was something important. We constructed a family of circular interval graphs. Right, it's an infinite family of graphs. And we said, you know, in general, they fall in here. Right? Maybe there are some there, but in general, they don't need to be line graphs. And maybe let me just remind you what a circular interval graph is. So you start with a cycle, you put sigma, and then you take a bunch of intervals on this cycle. Like this. And then you put vertices. So, and then you select some vertices of this cycle to be the vertices of your graph. This. And then you say two vertices are adjacent if some interval contains them both. So this is an edge, this interval, this is an edge because of this. Those three, they're all pairwise adjacent because of that. That was the intention of my drawing. Those two are adjacent because of this. These two are adjacent because of that. These two are adjacent because of that. Something like this. Okay. So these are circular interval graphs. And it turns out that basically, okay, so then what I said was there is a structure for Clawford graphs, but it's very complicated. Let me tell you about the structure of quasi-line graphs. And then I'll kind of wave my hands and say Clawford graphs is like that, but much harder. And finally, I should say this is all based on joint work with Folsey. Work we did from 2003 through 2006. Okay, so as it turns out, there are more or less two types of quasi-line graphs. One is closely related to this, and the other one I'll tell you in a minute. So let's keep those guys in mind. And now let me tell you another way to construct a graph. But first, I keep threatening you with generalized line graphs. So the time has come. Let's forget Clawford graphs for a minute, and let's just discuss something called generalized line graphs. Okay, so in order to tell you what generalized line graphs are, let me first tell you how I like to think about line graphs. So I have this graph, and now I'm going to construct it flat. So what I do is, me and every other person does, let's say this has edges E1, E2, E3, E4, E5. So for every edge, I put a vertex. So you see the spatial position of this vertex is the same as this edge. E1, E2, E3, E4, E5. And then if two edges share an end, I make the two vertices adjacent. So like E1 and E2 share an end, so I make these two adjacent. and so on. And then E5, it shares an end with E1, E4, E3, and E2. So E5, I just make a adjacent. All right. So far we'll understand what happened. So now what I want to do is generalize what I use to represent edges. Right. So in this picture, I replaced every edge with a vertex. I don't have to replace it with a vertex. I can replace it with a graph. So instead of having just one vertex called V3, I'm going to have a big chunk called eta of V3. Right, so it's the same for E4 and E1 and E2 and E4. So they're all just graphs. Eta of EI graphs on disjoint vertices. Okay, so then here I said if two, that's all, like in this picture, eta of V3 is just this vertex, but now it's a graph. And then I said, because E1 and E2 share an end, I'm going to make the vertex E1 adjacent to the vertex E2. So far it would say I should make this complete to that. But that's too much, that's not what I'm going to do. I'm going to choose a designated subset here that will be responsible for adjacencies through this end, and a designated subset that will be responsible for adjacencies through that. So in each at I, or at AI, there are two special subsets, right? So let's say EI has ends UV, then in eta EI, I'm going to have two subsets eta EI U and eta EI V. All right. So in the case of a line graph, everything coincided. Eta AI was the same as eta AI U, the same as eta AI. But now I'm kind of decoupling it. Okay, so then that's what I did. Let's say this vertical called U, V, W, Z. So then what? E1 and E2 share V. So I'll take eta of V1 and eta of V2. Line here because this is a picture. I'll take eta of V1 and eta of V2, and I'll make the V end of eta E1 complete to the V end of eta E2. Like this. E2 and E3 share the end W. So I'll take the W end of E4, the W end of E2, the W end of E3, I'll make them complete to each other. E3 and E4 share Z. I'll take the Z end of E3, the Z end of E4, make them complete to each other. E1 and E4 share U. I make the U end of E1 complete to the U end of E4. So now let me do E5. So E5 has two special sets, the end that corresponds to U and the end that corresponds to W. E5 shares U with E1 and E4. So I'm going to make their U ends complete to each other. And it shares W with E4 and E3. So I'm going to make their W ends complete to each other. Right?
Janowski, for the graph that corresponds to the edge UV, are there any vertices that do not get assigned to U or V?
Yes. So it's the ends, I call them the ends. The ends, they don't need to have union everything, and they don't need to be distributed.
Okay. And can they have any overlap?
They can overlap, that's right.
Okay, thank you.
Yes. Okay, so that's a generalized line graph. And, it's a way to build graphs. And it turns out it's sometimes useful. And it turns out that quasi-line graphs that are not circle interval graphs can be described as generalized line graphs. And I can tell you what this eta graphs are. All right. So let me write something down. Okay, I'm going to erase this. I'm sorry. There's some more questions. So let me call this, I don't know what's line graph type graph. Oh, actually, I know what it's called. It's called composition of linear interval strips. Sorry. What it means. Composition of linear interval strips. So that's just a class of graphs I'm describing to you, type of graphs I'm describing to you. And what that is, it's a generalized line graphs where for every E, eta of V is, I'm going to write something that I haven't defined yet, is a circular, is a linear interval graph. And I need to tell you what that means. But what I'm saying is, it's a generalized line graph, and I'm prescribing what kind of graphs you can use in eta. Right? I'll tell you what I'm prescribing, but the point of this is you can just use any eta you want. You have to use graphs like this. And eta EV is an initial shell click. And again, I'll explain what that means in a minute. For every E. Okay, so what did I just say? I said you can make generalized line graphs by using graphs from a certain family as etas, and you have to be careful what you allow to what ends are allowed to be, what you're allowed to put in the ends. Okay, so now I just need to fill in details. I need to say what these are, and I need to say what these are. But if you don't know details, then you understand what I just said. Okay, so what does it details? First of all, an linear interval graph, it's like a circular interval graph, except instead of a circle, you start with a line, right? Start with a line, intervals, this, have some vertices, and you make two vertices adjacent if they belong to the same material. To be a little bit more interesting. Okay, let me make this interval a little longer. Okay. And then, so every eta E has to be of this form. And then, what are the ends? Well, it's the, right, so to every interval becomes a clique. And then the ends are the clique that corresponds to the rightmost to the leftmost interval, and the clique that corresponds to the rightmost interval. So in this picture, the ends will be, this is one end, and this is the other. Right? So that's all it is. And you know, this is somehow very simple. The ends don't overlap, but you can make it more complicated. Okay. So now I claim theorem. Every quasi line graph is either, and I'll need a word here, so a circular interval graph or that composition of linear interval strips. There's a tiny bit of light here because in the graph that you start with to make a generalized line graph, you may have loops, and I didn't tell you how to deal with those, but let's not go that far. Okay, so there are two types. There are these and their circular interval graphs. Now, so what's missing? What's missing a thickening of factor A. So what's a thickening? What that means is you can so first of all, you can do something simple in a Clawford graph. If you've constructed a Clawford graph, you can take a vertex and replace it by a click. And you can check that it's still a Clawford graph. And if it was a quasi-line graph, it's still a quasi-line graph. And another thing you can do in some very specific circumstances, you can take two vertices, you place each of them by a click, and then put an arbitrary vector graph between them. And that's called a thickening. So I don't want to talk too much about it, but it's some other little trick you can do. So you take, basically it's graphs of these two types, plus the slight manipulation you can do to them. All right, and that's all quasi-line graphs. So then what happens with general Clawford graphs? So it's the same kind of thing. There's one big class which are generalized line graphs with prescribed strips, except here I had one type of strip. There we have 15 kinds of strips. And then there are a couple of classes which are not generalized line graphs. One of them is circle interval graphs, but there are some, but it's somehow same, same structure of a theorem, but with more options. All right, so I think maybe this is enough about Clawford graphs. Questions? Okay, and again, if it's something you're interested in, I recommend reading the quasi-line graph paper. So it's a series of, I think, 7 papers, and one of them is the structure of quasi-line graphs, and that one you can read. And then there's a paper that describes all Clawford graphs, which is very hard. I mean, if you kind of know where to look for information, you can find it, but I really recommend looking at the quasi-line graph paper first, just to get a feel for the concept. All right. Okay, and now I'm going to switch to the last topic I want to talk about. All right, so switching gears completely, if you haven't been paying attention, now it's time to come back. Now we're going to talk about Kaibabs. And what does that mean? So in the first lecture, I talked about perfect graphs, which means for every induced subgraph, the clique number and the chromatic number are the same. But now we're going to relax this notion. Now all I want is that the chromatic number is bounded by a function of the clique number. So family C plus graphs, and let's make it closed under induced subgraphs because it's more convenient. Closed under induced subgraphs. Let's say C is chi-bounded. It exists a function f depending on C, so that for every graph in C, the chromatic number of G is at most this fc of the clique number. Right? And we call this fc a chi-bounding function. Fc is a chi-bounding function. All right. Now, notice I said here a chi-bounded function. This f is not meant to be the best or anything like that. It's just some function that satisfies this. And there's a study of what's the best chi-bounding function, what the correct dependency between the clique number and the chromatic number. But that's not what I'm going to talk about. I'm just going to talk about when can you find some function. Okay, so like I said, it's a generalization of perfect graphs. Why? Because the class of perfect graphs is a chi-bounded class where this F is identity function. Graphs. Chi-bounded is FC thing, the identity function. Right? Chi equals on them for every perfect graph. Okay, but here we're asking for something much less strong. So one thing you might notice, this definition is only interesting when C is an infinite class of graphs. Right? So C is finite, and take just some numbers and take the biggest number and we're done. So let's convince ourselves that this is meaningful. What do I mean by that? I mean that this is not true for every graph. That there's some, if I look at a class of graphs where such a function exists, there's something special about it. If I just look at all graphs, then it's not a chi-bounded class. Theorem, class of all graphs is not chi-bounded. All right, and specifically, there exists, so for every k, there exists g sub k such that chi of g is k and omega of g is 2. You can find triangle-free graphs with arbitrarily large chromatic numbers. So that means you're not going to be able to bound the chromatic number as a function of clique number. All right. So let me show, this is a pretty construction, so let me show it to you. I mean, there are actually many constructions, but the one I know and like is the Michalski construction. And it's spelled something like this, but possibly not exactly like this. My spelling of Michalski's name keeps improving throughout my life, but I think there might still be room for further improvement. Okay, so here's the construction. So this is G2. Okay. The clique number is 2, the chromatic number is 2. This is G3. So the clique number is 2, the chromatic number is 3. Now let's make G4. So G4, it's a bit more complicated. So you start with a copy of G3. So constructing G4. So I started with a copy of G3. And now I'm going to clone every vertex. I'm going to replace every vertex by a copy of itself, a non-adjacent copy of itself. So like this. And the copies make a stable set. There are no edges between the copies. And then I'm going to add another vertex and make it adjacent to all the copies. So this is G4. And now this is a general way in which you can construct GK plus 1 from GK. Start with GK plus 1, copy every vertex, and now add a new vertex complete to the layer of copies. Let's draw here a schematic picture of GK. So here's how you make GK. You start with a copy of GK minus 1. Then you make a copy of every vertex, but the copies, right, they have the right neighbors downwards, but there are no edges between them. And then you make the new vertex. All right. And it's easy to check that they're triangle free. There's a trick to checking that the chromatic number goes up, but it's not hard. It's a nice exercise. Okay, so this tells you that they're graphs with clique number 2 and arbitrarily large chromatic number. There's in fact questions about that. So there's in fact a much stronger theorem of Erdős, which I'll write down now. theorem, for every k and g, there exists a graph GKG such that the chromatic number is k and the girth is at least g. So what's girth? Girth is the length of the shortest cycle. That's the shortest cycle. So Michelski construction constructed GK4, like a triangle free graph has girth at least 4. But Erdős can do this in greater generality. Right? You can build graphs with arbitrarily large girth also. Okay, and I'm not sure how to prove this, but it's a probabilistic proof. Okay, so now we convince ourselves that there are a lot of families that are not chi-bounded, including such nice families as triangle free graphs or graphs of high girth. So then one should ask, what families are chi-bounded? So forbidding reach, maybe a little bit more precise about this. So for which h, form of h form of h is kind of. And here, form of h means a family of graphs, maybe finite, maybe infinite, and form of h means g such that for every hi in h is not the subgraph of G. Right? So in kind of normal people's words, what do I need to exclude to produce a chi-bounded field? And the first question is, what if I exclude one graph? You know, I know excluding a triangle is not enough, or excluding a C5 is not enough because graphs with girth 6 are not chi-bounded. But what can I exclude? So question, for which h when is form h? When I just exclude one. Well, there's lot you can say, because I claim we can already prove that if form h is chi-bounded, then h doesn't contain a cycle, because of this theorem of Erdős that I just showed you, right? H is some fixed graph. So if h contains a cycle, then the class of all graphs with girth bigger than the size of h does not contain h, because h contains a cycle. And on the other hand, Erdős's theorem tells you that they're not chi-bounded. Okay. So if form h is chi-bounded, then h is a cycle. Okay, so that throws out a whole lot of graphs, right? And the proof is that. And it's a conjecture. It's a conjecture of Jefferson independently Sumner. It's an east-west conjecture. It's Jefferson conjectured it in Hungary, and Sumner conjectured it in the United States. And for years, they didn't know about each other's conjecture. But now we call it the Jefferson-Sumner conjecture. So, conjecture, Jefferson, and independently Sumner. for every forest H, there exists F sub H, so that if H is not a subgraph of G, then chi of G is most F sub H of omega G. Right? So in other words, another way to say this conjecture, for H is chi-bounded if and only if H is a forest. And the only if part is easy, and the if part is open. And it's known for some trees, but I'll tell you all the trees it's known for. Okay. So now let me say something else. So what if I don't exclude one graph? What if I exclude many graphs? Like with perfect graphs, we excluded all long holes and all long anti-holes, and the result was very nice. The result was the chi-bounded class with chi-bounded function identity. So what if I go in the same direction and I try to exclude some whole lengths? And this is an idea of Jefferson in 1985 wrote a beautiful paper called "Some Problems from the World Surrounding Perfect Graphs." Now, it's such a lovely title, right? How can you not want to read a paper? It's called "Some Problems from the World Surrounding Perfect Graphs." And what he wrote about is precisely these concepts, and specifically getting chi-bounding functions for graphs where whole lengths are restricted. So let me write something down about that. So now I have I is a subset of natural numbers, and let's say HI or CI are all graphs G, so that G has no induced cycle with length Ni. So if C is an induced cycle in G, then V of C is not infinite. In other words, I forbid some cycle length, some induced cycle length, some whole length. What do I forbid? What I forbid is I. And so that's saying if there is an induced cycle in G, then its length is not infinite. All right? And so then we can ask which I is CI Kaibabs. And Jefferson made 3 conjectures about it, and by now all 3 of them are theorems. So one is if I is the set of odd numbers. Then you get a chi-bounded class. So you forbid all odd holes. Triangles don't count. And if you forbid all odd holes, including triangles, or all induced odd cycles, including triangles, that's a bad graph. That's a theorem. But he said forbid all odd holes of length at least 5. All odd induced cycles of length at least 5. Right, so this is kind of directly from the world of perfect graphs, because it's half of what makes a graph perfect. There you forbid this and this in the complement. But he said, let's just forbid this. Then the second one was, let's forbid all long induced cycles. Now how to say this? The numbers of lengths listed. So all so what he forbids are lengths that are bigger than that. And then the third one was a common strengthening. Forbid odd holes which are long. Right? So I is odd numbers bigger than that. And then maybe I'll write here, ICL. So he conjectured that if you forbid, so he conjectured that all of those produce chi-bounded families. That if you forbid all odd holes at the chi-bounded family, if you forbid all long holes at the chi-bounded family, and if you forbid all odd long holes, so you're allowed any even hole you want, and you're allowed any short hole you want, but long odd holes are forbidden. That gives a chi-bounded family. And these conjectures were open for a long time. They were open for about 30 years, I think. Now, of course, it's enough to solve 3, right? You can save some time and not try for 1 and 2, but just solve 3. But chronologically, the way it went, it was 1 and then 2 and then 3. So the conjectures of Jefferson, the theorems are, the first one is Scott and Seymour. The second one is me and Scott and Seymour. And the third one is me, Scott, Seymour, and Sophie Shkroko. So, but by now they're all done. This is, and it's all like between 2015 and 2018. Exactly when. All right. So what? So I won't show you any of these proofs because, like, they're not super hard. They're, you know, again, these are 15-page long papers. These are papers that you can definitely read if you want to know the proofs. But still, it's a bit too much for the last 22 minutes of this course. But what I will show, what I hope to show you, is a common strengthening of 1 and 3. A common weakening of 1 and 3. A common strengthening of 1 is 3 and 3 is 3. But what I mean is a common weakening of 1 and 3. So our goal for the rest of today, it's actually a theorem of Alex Scott from the mid-90s, back in 1990s. Yeah. Scott. I'll write 1995. I don't really mean 1995. I mean after 1990 and before 2000. So for every L, there exists F sub L, so that if G has no odd hole and I should say no C5, and no hole of lengths at least L, then I of G is at most F sub L of omega G. Right, so what this tells you is that if you forbid C5 and no long holes, then you get a chi-bounded class. And so let's keep this theorem in mind because I hope to get to its proof. But before I do that, I want to show you a theorem of Jefferson. So he made these conjectures, but he also proved something else. He proved that if you forbid a long path, then you get a chi-bounded class. And that's very, very nice, and it's a building block for everything else. You do that proof many times under many different circumstances, it comes out. Any questions, by the way? Theorem of Jefferson. For every t, there exists f sub t, so that if G is PT free, meaning doesn't have an induced path on T vertices, then chi of G is at most F sub T of omega of G. All right, so let me show you the proof. Some proof. Okay, so it's enough to prove it for connected graphs. Do this for every component separately. So start with any vertex. Oh, and also I'm going to do induction on omega. So what I mean, I'm going to, so what do I need to do? I need to define ft of omega. And so I'm going to assume I've already defined it up to the current value of omega, and I'm going to define ft of omega. So we find ft of 1 up to ft of omega. And now I'm working with the graph with clique number omega. Now we're ready. Take a vertex, take its neighbors, and then you look at components of the rest of the graph. Okay, so first of all, this bit has small chromatic number because the clique number went down, right? You don't have a clique number of size omega here because then at this vertex has a clique number of size, that's a clique of size omega minus 1. So this I can color with ft of omega minus 1. So that means one of these has large omega, I'm sorry, pardon. One of these has large chi, because if each of these has chi 2 to the 2 to ft of omega minus 1, then I can bound the chromatic number of the whole graph. So let's say this guy has huge omega. I'm sorry. Let's say this guy has huge chi. Now remember the graph was connected. That's why I'm using the graph was connected. So somebody here had a neighbor there. Okay, so take him, take all his neighbors. This bit has small chi because it has small omega. So when I look at components of the rest, one of them has big omega, a big chi. But this was a component, this was connected. So there's an edge like that. Look at his neighbors in that component. This bit has small omega. So some component there has big chi. So I can get another edge. Now what am I building? I'm building an induced path, right? 1, 2, 3, 4, 5. And so on and so forth. So if this was really huge, if I can repeat, if omega of the whole graph was really huge, if I could repeat this as many times as I want, I would build a path, an induced path of length longer than t. And I believe the number that works is chi at most omega to the t, or something like that. And so you can check that if chi is bigger than omega to the t, then this argument will give you a long path. Okay, so this is a proof. And what's nice about this proof that we can extract a technique out of it. What I want to extract out of it is this construction of what we call a Jefferson path. So what's a Jefferson path? It's a path into large chi. So it's a path, it starts with a vertex, and then it's an induced path, and then the last vertex, and then there's a subset or subgraph here with big chi, so that the last vertex of the path has neighbors there, but nobody else in the graph has any neighbors there. And that's what we constructed here. We started with this vertex, and we kept walking in the direction of big chi. We call it walking in the direction of big chi. And what this theorem really shows you that if omega is bounded and chi is huge, but that doesn't happen for smaller omega, then you can get a Jefferson path which is as long as you want. All right. So if chi, if for every g with for every induced subgraph of G, subgraph, let's say H of G, with omega of H strictly less than omega of G, we have that chi of H is bounded, right? Most n, but chi of G is much, much bigger than n, then G, then every vertex of G starts long Jefferson path. Now, how long is long? Well, that depends how much bigger this is, right? If long is t, then this much, much bigger depends on t. All right. Okay, so let's remember this. Let's remember that in a graph where I've already dealt with subgraphs of smaller omega, but the whole graph still has a huge chromatic number, I can choose Jefferson paths. However, I can construct Jefferson paths. However, for every vertex, I can start a Jefferson path. I can start a Jefferson path from it. So now let's prove Scott's theorem. And remember, what we're proving is that if you forbid C5 and you forbid all long holes, then the chromatic number is bounded as a function of the clique number. So we know that if I forbid, so we know that if I look at the neighborhood of a vertex, I can always say the chromatic number is small because the clique number went up. But the first thing I want to prove is that if you forbid C5, then you can also bound the chromatic number of the second neighborhood. So step one, G is no long hole and no C5, then chi of the second neighborhood of the vertex is at most some function of omega. And again, I'm going to assume that I've dealt with everything for smaller values of omega, and I'm going to construct f for one given omega. So here's what. So first of all, what's the second neighborhood of the vertex? You take a vertex, you take its neighbors, and then you take the neighbors of the neighbors. All right. So this is called N2. This is called. And clearly, the chromatic number here is at most f of omega minus 1, right? Because you don't have a big clique number. So now let's bound the chromatic number of this. Well, so this has small chromatic number. Let's color it. Let's partition it into these many stable sets. Right? So now this is a partition of this set into this many stable sets. Now that we partition this by their parents. Everybody here has a neighbor upwards. So let me have people who have a parent here, then people who have a parent here, people who have a parent here, and so on. And sometimes there's a choice, right? Maybe somebody has both a parent here and a parent there. Then I don't care. It doesn't matter where you put it. All you care is that everybody is assigned to a set that has a parent in the appropriate place. And so I'm not saying like there are no edges like this. I'm just saying everybody here has a neighbor there. So this is so far a partition of this bottom into f of omega minus 1 sets. And now claim each of these sets I can color with not very many colors. And if I have not very many sets and each of them I can color with not very many colors, then I win. So why is that? Well, I claim a set like this cannot contain a clique of size omega. Because suppose in here there's a clique of size omega. Well, they all have neighbors up there. Take somebody here with as many neighbors in this clique as possible. Here it is. Is it possible that he's complete to this clique? Well, it's not possible because there's no clique of size omega minus 1. So he definitely has a non-neighbor. This guy has a neighbor up because that's the definition of this set. Could it be that he is complete to all of those? Could it be that he is complete to all his neighbors in here? No, because he had maximal neighbors. This is a non-edge. This is a non-edge because it's a stable set. But now we got a C5, right? 1, 2, 3, 5. So each of these we partition to f of omega minus 1 sets, but each of them has chi at most f of omega minus 1 because each of them doesn't have a big clique. So that means we prove that chi of n2 of v is at most f of omega minus 1 squared. All right. And so that's for the sphere, right? That's for people of distance exactly 2. And if you want all of this, well, that's easy, right? Because this chromatic number we know is small. So the chromatic number of all of this is at most f of omega minus 1 plus f squared of omega minus 1. All right. So we proved the first step. We proved that in the graph in our class, second neighborhood has bounded chi. First neighborhood is for free. The second neighborhood we had to work. And we used that there's no C5, and we used induction. Okay? And that's the only place where we use that there's no C5. Questions before I erase everything? So now let me prove that if G has no long pole and for every V in G, chi of the second neighborhood of V is at most some n, then chi of G is at most a function. Right, and that will be enough because we already proved the graphs in our class have this property. But I just want to separate these two and to emphasize that here I'm not using that there's no C5, I'm only using that. So if you could get that under assumptions different from no C5, then you could still prove the theorem. And that's in fact how the proofs of the second and third conjecture of Jefferson work. Or actually the third, that's how the proof of the third conjecture of Jefferson works, where we exclude long poles. The second and third. Okay, anyway, so let's prove this. So to prove this, so here we only thought about second neighborhood. Here I'm going to start with the vertex and do what we call a layering. We partition the graph into layers by distance from this vertex. Everybody has a neighbor one layer up, doesn't have any high neighbors. And you can notice that you can, repeat colors. You can color all the even layers with the same colors and all the odd layers with the same colors. So that means that some layer has huge chromatic number. This layer has huge chromatic number, and that means it has a component with huge chromatic number. Chromatic number is the maximum chromatic number of component. And this is short, this is like another couple of minutes. So this is connected and large chi. So now let's choose another vertex here with neighbor. That's still connected with large chi. And now I'm going to get the Jefferson path. So I'm going to look at the graph consisting of this box plus that vertex. And I'm going to get a Jefferson path starting at this vertex. So what does it mean? It means I can walk for a long time. How long? Well, however long this is. Let's say long as L. So it will walk for L steps. And then there's still, it's a little bit bigger. There's still a large connected set here with large chi. And he has neighbors. Okay. That's what the Jefferson path is. So now, what do we do? Now, this is a path of length cell. Everybody's second neighborhood has bounded chromatic number. So if I delete from here the second neighborhood of all of these vertices, there's still going to be something left because the chromatic number of this is huge and the union of the second neighborhoods only has chromatic number L times N. So let me delete all the second neighborhoods. Here they are. Union of N2, 3, and plus. And there's still something, the math is okay, I'm just trying to find a better picture. So let me not put a big X on it, let me just say it's here. And there's still something left there. Okay, so let me walk from this vertex to that vertex inside that set, which I can do because it's connected. Possibly walking through this bit. Here. So he is not in the second neighborhood of anybody there. This I don't know. Okay, but he does have neighbor upwards because that's how layings work. And then I can find a path between these two somehow through there. Maybe they're already adjacent. Maybe I can connect them through one layer up. But in the worst case, there's a path between them like that. And maybe that works. So now I claim I'm doing pretty well because this thing that I just constructed, it's starting to look like a long hole, right? It has this long path, long clean path, long induced path in it. And then there's some completion. And if only I could, and maybe I'm shortcutting a little bit somewhere, like shortcutting like this or something. But if only I could prove that all my shortcuts don't ruin this long path, that would give me a long hole. So let's prove that. I'm not going to do it carefully, but you can convince yourselves that the only possible, so after I've done this shortcut, the only reason this thing is not induced is because he might have neighbors. And all the rest is too high. This is a Jefferson path, so all of this is anti-complete to all of that. So the only danger is that he has neighbors. But can he have a neighbor here? And the answer is no, because this vertex is not in the second neighborhood of anybody like that. So I don't have a 2H path like that. So this guy, in fact, is safe from the point of view of the black path. He does not have any neighbors to the black path. He might have chords to here. I don't know about that. These are allowed to be in, I don't know anything about those vertices. But I know that this guy does not have any chords to the black path. But now that's a win, right? You follow the black path until his first neighbor. You're guaranteed to still have your black path, all of your black paths. And then you complete like that. And what did you get? You got a follow length at least L. And you're done. And so we proved Scott's theorem. And let me stop here. Thank you very much.
Thank you for the lecture. So maybe questions. Let me stop the recording.
Okay.